the engineering application of the low cell, not low cell, the orthotropic materials. So here we are given those kind of pieces of information and Young's modulus in the unit of the GPA. And we have the one measurement and we want to find the other four. So from here we can try is this. Basically, the first one you identify in this matrix, the information we are given is this. And let me highlight the given informations with color. And then xz, new xz is here. And we are given xy is here. And we are given zy is here. Okay. So we are given those information that is highlighted in blue color here. To solve for, also we are given is these numbers, and we want to solve for other things. This problem basically is this. This is the material. And these are x directions and y directions and z directions. Okay. This is orthotropic material properties, and this one is under loading. On the uniaxial loading in x directions. Okay, on the uniaxial loading in x direction, in this way we measure the strain for that deformations. So, because this is a uniaxial loadings, and in y and z directions, there's a no loading, so that means this no loading, that means the stress equal to 0 right away. Okay. And so now basically we, a typo here, sigma x, sigma y, and sigma z. Okay. So right now for this one, we know this one equal to 0. And this one equal to 0. Okay. So from here you can clearly see how many, basically here we have two strain components and one stress components to determine from these three equations. So three linear equations, three unknowns. Assuming if we know this matrix, then basically we can solve for this. Okay, so under these situations, we know the Young's modulus. But the question is this: we don't know this one, we don't know this one, and we don't know this one. Okay. Poisson ratios, mu yx not equal to mu xy, not necessarily. Okay. So here we utilize the symmetry. The symmetry basically is this. We're going to utilize the element. This one, this value equal to this value by symmetry. The similar way, this value equal to this value equal to that value. Okay. So using this information, we will be able to completely write out the numbers for this matrix. And so using the symmetry, of the compliance. Matrix, and we are able to find out the yx equal to y equal to ex mu xy. Okay, and similarly for the other two equations. Okay, so the similarly that means this one, this element equal to this element. The values, and this value equal to that values. Okay. So keep everything in mind here, then we are able to finish all the writings. And so for example here, we are given this one. You can calculate with this number and with the Young's modulus, this one can be determined. Okay, can be calculated. In a similar way, this number can be calculated, this number can be calculated. So the whole contents of the compliance matrix is determined. So with that number determined, then I can give you the result directly. The remaining simply is to solve for a linear set of the equations, and that can be done either by hand or by the MATLAB. So here the sigma x equal to 44.6 kPa, and then sigma z equal to 3.5 MPa. Okay, and then epsilon y. I don't have that calculations. I don't know how much x. I think this one.
Isn't sigma z 0 already?
Yeah, it's not this one. I think that one, I don't have the calculation, maybe leave that alone to you. Okay. And from here, I like to have using the same example to exercise a different boundary conditions. So this one is on your own for calculations. Okay. And using this one, I want to exercise for another boundary conditions. The boundary condition is this. So this will be the exercise 2 with the same setting. And for this one, in addition to the uniaxial loadings, then this material basically is constrained in the z directions. So you can imagine there's a two rigid plate lift in the z direction to confine these objects from deformation in the z directions. Okay, so basically you could imagine we have we constrain the z deformation. So under this case, and I would see the epsilon given. Okay. So for these new settings, basically here in the z-plane, that is constrained without any movement. So under any loading, you could imagine basically this block is being sandwiched between the two plates, and under this kind of the uniaxial the loading. So from here, all the lateral deformation will go to y direction only. And because z direction has been constrained from any movement, so you could imagine, suppose without this rigid constraint, the material can free to deform in z. But right now the z direction has been sandwiched, so the material will experience the stress in the z direction, right? Okay, so here for this case, the sigma z won't be equal to 0. So now for this case, we are given is this, and we are given is epsilon z, this one equal to 0. So this one, we're looking for this one. Okay, so again, here, how many numbers we're looking for? 1, 2, and 3. So for this one, then we could have the calculation. Again, that is on your own, you can calculate it. Okay? Then the follow-up, the example is I want to show another example. So Max, we can have another video.